Welcome to this explainer. Today, we're diving into a genuinely incredible 5-year experiment. It actually proves how an ancient building material might just hold the ultimate chemical recipe for modern, sustainable architecture. We're going to look closely at the hidden chemistry of soil. And note, we're talking about carefully engineered soil here, not just the dirt you'd find in a backyard. We'll see how a tiny, almost imperceptible tweak in its stabilizing ingredients can create structural materials that easily rival traditional options, all while drastically reducing our environmental footprint.
Here's our roadmap for today. We'll quickly cover fired bricks versus earth blocks, stabilizing the soil, the 5-year experiment, the cement-lime synergy, micro-level waterproofing, and finally, a sustainable foundation.
Section 1. Fired bricks versus earth blocks, and specifically the carbon cost. Let's start with a severe environmental problem traditional construction is facing today.
Now, it's pretty fascinating to realize that building with earth, it isn't some new eco-trend at all. It's actually a practice that dates all the way back to Mesopotamia, roughly 6,000 years ago. For millennia, humans have used the soil right beneath their feet to build homes, monuments, even entire cities. But in our modern era, we've heavily shifted toward energy-intensive materials, and we've completely sidelined one of the most abundant resources on our planet.
And comparing these two approaches brilliantly illustrates why that shift is such a problem. When we compare standard fired bricks to unfired earth blocks, the environmental contrast is just night and day. Fired bricks have to be baked in kilns at extremely high temperatures, which requires massive energy consumption and leaves a very heavy carbon footprint. But unfired earth blocks, they can be sourced locally and pressed without ever seeing a kiln. The result is that they release a staggering 80% less carbon dioxide into the atmosphere. 80%! That is a massive leap forward for sustainable building.
Moving to Section 2, stabilizing the soil, engineering earth. Because of course, you can't just pack loose soil into a wall and expect it to hold up a modern roof, right? We have to engineer it.
Which brings us to CSEBs, or compressed stabilized earth blocks. These are highly engineered, unfired masonry units. Instead of baking them, we manufacture them using proper soil grading, extreme physical compaction, and, this is the absolutely crucial part, chemical stabilizers. This three-pronged approach gives us high-volume stability, water resistance, and incredible strength without ever needing an energy-intensive kiln. Think about the very specific recipe researchers developed for the perfect baseline earth. To form a solid structural skeleton, they optimized a reconstituted soil mix that relies heavily on sand, about 76%. Then, they included just enough non-expansive colonite clay, around 11%, to act as a natural binder. It is a very deliberate, highly controlled foundation. Again, this isn't just everyday soil, it's practically a science in itself.
Section 3. The 5-year experiment, the stabilizer dilemma. Because having the right soil is really only half the battle.
To find the absolute best way to chemically stabilize this specific soil, researchers launched an exhaustive 5-year experiment. They created 3 distinct test series to really challenge the industry standard. Now, the standard for this type of soil is usually 8% cement, which they call their S1 series. But cement is super carbon intensive to produce, so researchers wanted to test if combining lime, which is a historically slow-acting stabilizer, with fast-acting cement could actually outperform cement alone. They tested S2 with 6% cement and 2% lime, and S3 with an evenly balanced 4% cement and 4% lime.
The physical creation of these blocks was rigorous. The soil, water, and stabilizers were thoroughly mixed, and these fresh earth blocks were meticulously pressed using an Astrum machine to guarantee a uniform, high density. Then, they were carefully numbered and cured under shade. Doing it this way allowed researchers to meticulously track their long-term wet compressive strength over a period of years, not just days or weeks.
Before final testing, the prepared blocks had their indentations, or frogs, as they're called in masonry, filled flush with a 1-to-1 cement mortar. They were getting prepped for the ultimate trial. Before being crushed in a universal testing machine at very precise milestone dates, they were entirely immersed in water to test their wet compressive strength, which really is the truest test of a block's real-world durability.
Section 4. The cement-lime synergy, the race for compressive strength. Now we dive into the fascinating chemical synergy revealed by all this testing data, and honestly, this is where the story gets incredibly compelling.
Think of this chemical reaction like a literal race. Early on, up to the 4-month mark,
The sprinter of our experiment, cement, takes a massive lead. In the S1 blocks, with 8% cement, the cement quickly hydrates and binds all those sand particles together. If you were only looking at the short-term data, you'd probably walk away thinking cement alone was the clear winner.
But as the timeline accelerates from 6 months to a year, 2 years, and all the way out to 5 years, well, the marathon runner enters the chat. The lime begins a slow, continuous polylytic reaction. Over months and years, the lime raises the pH of the moisture in the block, dissolving the silica and alumina in the clay to form incredibly strong calcium aluminosilicates. It's this beautiful slow burn that just continues to build massive long-term strength, long after the cement has finished its sprint.
The ultimate payoff happens right at year 5. The S3 series, that's the one with a perfectly balanced 4% cement and 4% lime, just utterly dominates the standard mix. It reaches a massive 7.2 megapascals of wet compressive strength, compared to just 4.9 for the cement-only mix. The cement provided the early structural integrity, which basically gave the lime the time and the perfect environment to work its long-term chemical magic on the clay.
Guys, that is a staggering 47% increase in final strength. 47%. And the crazy part, this wasn't gained by adding more stabilizer. It was gained simply by allowing the optimum combination of cement and lime to work together synergistically. It proves that unlocking massive long-term durability doesn't require more brute force chemicals. It just requires smarter, more patient chemistry.
But wait, what actually happened to the S2 mix, the one with just 2% lime? Crucially, that middle mix lost strength compared to the baseline. Why? Well, it's because of a chemical phenomenon called lime fixation. The clay in the soil actually has a natural appetite for lime, and it absorbed that entire 2% immediately. It just ate it all up, leaving absolutely no free lime left over to trigger those incredible long-term strength-building reactions we saw in the S3 mix. It's a textbook example of why getting the exact ratio is so critical.
Section 5. Micro-level waterproofing. Because this chemical synergy isn't just about raw crushing strength either, it fundamentally changes the internal microstructure of the block itself.
Those continuous cementitious reactions we just talked about, the long-term calcium aluminosilicates forming, they actively filled in the interconnected microscopic voids inside the block over the course of those 5 years. And because those tiny pathways were blocked by the new chemical gels, the S3 block's water absorption plunged all the way down to a highly durable 7%. In the real world, that means way better resistance to rain, far less internal erosion, and a drastically longer lifespan for the building.
Section 6. A sustainable foundation. So, bringing it all together, what is the ultimate real-world application from this 5-year scientific journey into soil chemistry?
By utilizing the true chemical synergy of cement and lime, builders can erect significantly stronger walls while actually using less total stabilizer volume. The cement handles the short-term binding of the sand, and the lime handles the long-term stabilization of the clay. This synergy directly lowers mass production costs, drastically reduces our energy consumption by avoiding the kiln entirely, and significantly shrinks the environmental footprint of the entire construction industry.
It leaves us with one incredibly provocative thought to end on today. If an optimized mix of local earth, a little cement, and a little lime can synergize over time to build a far stronger, cheaper, and greener future, why are we still firing bricks? Thanks so much for joining me on this explainer. Keep questioning the world around you, and I'll catch you on the next one.